Hi, welcome back to the statics review sessions. In this session, you learn how to find a resultant of a non-coplanar force system, or how to find a resultant of a force system that is in 3D. I will first talk about how to represent a force in Cartesian vector form, and there are three methods to do that. If the force is represented by its direction angles, or the force is represented by its projection information on the xy plane, or using the position vector. And then finally, wrap it up with an example, numerical example. A force can be represented by its direction angles, and these angles are nothing more but the angles formed between the main Cartesian axis and the vector itself. So we give the angle alpha that is formed between the x-axis and the force vector, beta between the y-axis and the force vector, and gamma between the z and the force vector. These angles are measured from the positive side, so it goes from 0 all the way to 180 degrees. This will also be important to see whether this component is in the positive direction or it's in the negative direction of the axis. The same goes, alpha goes from 0 to 180 and gamma goes from 0 to 180. We'll see this in the examples how to do. So how can we write a relation that between the components and the angles that will give us at the end the force in Cartesian vector form? If you look at these triangles formed in 3D between the component and the force vector, the angle is actually set in a cosine relation. So the force component is adjacent to the angle in a right angle triangle in 3D. So in that case, you have that force component. If we need to write that, then you have cosine alpha as the fx component, which is adjacent to the angle over the force vector. Cosine beta is the force component in the y-axis over the force vector, and cosine gamma is the same fz over the f. These angles mathematically has to satisfy the relation between them where the cosine square alpha plus cosine square beta plus cosine square gamma equal 1. This equation or formula will help you a lot in finding if two of the angles are given. You can solve it for the third one and find the third angles. Notice here the cosine squared, then you might have two angles. One is less than 90, one is greater than 90. You have then to look at where to the figure and see where exactly is that direction of the component, and we'll see this in examples. The following is how to relate that is that we have these relations, angles relations. The following is that we can then write that the unit vector is nothing more but the vector over its magnitude, as we discussed in the previous session. Or we can write the force vector over its magnitude in the ij key form. You notice here that this f of x over f is nothing more but a cosine the alphas, which means that we can just simply write the unit vector using the direction angles. And this way, if we need to find the force in its Cartesian vector form, so if the angles are given, then and the force magnitude is given, then you can find the cosine, the angles, and then just find the force in Cartesian vector form by multiplying the force magnitude by cosine the angles, which will get you the force components. And this is the first method of representing a force in Cartesian vector form. The second method is using a projection information. So what is that? If you just think of this box that is composed of the force vector, and it is its component, it's f of x, y, and z components. If this force is projected on the xy plane, we give it the f prime. And if you look at these two triangles, this dark blue and the light blue triangle, that is this dark blue triangle is formed between the x component, the projection of the force on the xy plane, and the y component of the force. And the light blue is composed of the force vector, its projection on the xy plane, and the z component. So we can just start by writing for or using this small triangle and write that this f prime using Pythagorean theorem is with the knowledge of f of x and f of y, and using this light blue triangle that is composed of the force, its projection on the xy plane, and the z, then we can write that this force is f prime squared plus fz squared and all to the square root. So we can then substitute for the value of f prime and then write the final is the magnitude of that force is given by the sum of the squares and the square root out of that. Using this method, we can then represent the force in Cartesian vector form. So problems like that, it will be given, the force magnitude will be given, and then the angle formed between the force and the projection on the xy plane, and also the angle formed between the projection of the force and the x or the y. Using these angle, then that's a two right angle triangles, then you can simply find the three components and represent the force in Cartesian vector form. So finally, using the position vector to represent the force in Cartesian vector form. A position vector is a vector that connects 2 points in space in 3D. So this position vector, always given to it as r, connects the points A to B. The position vector is represented by Rx component, Ry component, Rz component. So the Rx is nothing more but the difference of the coordinates, the x coordinates of B minus the x coordinate of A. This is the Rx. Ry is the difference between the y coordinates of B and the y coordinates of A. And z is the same as the difference between the z coordinates of B and the z coordinates of A. We can simply also just measure the distance between that goes if you just draw this path going from point A to B, whether you go from this way or you go from this way or anywhere, then you can just write the form of the position vector in its Cartesian vector form. The magnitude of the position vector, which is the square root of the sum of the squares of their components, is nothing more but the distance between these 2 points. So if we have the position vector and we have the magnitude, then you can remember that the unit vector is represented by the vector of its magnitude, which is also the force vector of the magnitude. So problems like that, or examples, or questions like given the force magnitude and some dimensions that shows where the coordinates of these 2 points of a vector, then you can then write the position vector, find its magnitude, and then finally multiply by the force magnitude, then you can get the force in Cartesian vector form. We'll see this in the next session when we work more with the position vector. So a force, as in 2D, a resultant force is sum of all the components to get a force in Cartesian vector form. So the force resultant force component, resultant force vector, is sum of the forces in its x component and a y component and a z component, which means that whenever that you need to find a resultant force in 3D, you need to represent all forces in the force system in Cartesian vector form and then add the x, y, z component, and then later find the angle, the direction angles to find the direction of that force component. So let's start by this numerical example. This example is represented by given by 2 forces. One force is given by its magnitude and direction angles alpha, beta, and gamma. Notice here that alpha here is 120, which means that it is in that quadrant where the x component has to be a negative. and beta is 45, gamma is given as 60. The other force is represented by the slope of the force, 3, 4, 5, and the magnitude. The slope is can also represent this triangle that is formed between the force and its projected force on the xy plane. So the first step, as we did in 2D, is to represent these two forces, to get the result and represent the two forces and its xyz form. So let's start with this force F1. The first step is always when you see a force represented with these two triangles, is to try to draw these two triangles in 2D. So we start by drawing always the force triangle. So you have this force and the projected force on the xy plane F prime and the z component of the force, where we know that the 3, 4, 5 is the slope of that force. The second triangle we can draw is this light blue triangle that is formed by the Fy, this is the y component, and f of x, and finally the f prime. So if we need now to, given in this triangle, you have only the angle. So these three are not given. You have only the angle. But in this triangle, you have the force is given in magnitude, the 600, and given also the slope at 3, 4, 5. So we can start by finding the f prime and fz, which will help us in later to find using f prime, the f1x and f1y. F of z. To find f prime is to use the 4 over 5. So we can write then the relation for fz, which is the force multiplied by the 3 over 5, the vertical. And notice here that f1z is going down, which means that it has to be a negative. And then f prime would be using the 4 over 5. Then you can just use this f prime, find first f prime, and then multiply it by sine to get the x component, because the x is the opposite to the angle, and using the f prime to find the y component, which is the adjacent to the angle here. So finding those or writing in this form, then we can just represent this is the force in its Cartesian vector form after doing the multiplication, and notice always the negative sign of that force. Followed by that is how to represent the force, the other one, with the Cartesian vector form. F1 is represented by the direction angles. So simply is multiplying the cosine, the angles, by the magnitude. Alpha is 120, beta is 45, and gamma is 60. Multiplying it by that, then it gets you the force in Cartesian vector form. Now, please pay attention to that sign. So because we use the cosine 120, then we get the answer in negative. If you, for example, sometimes it would be given the 60, which is measured between the force and the negative sign, then you have to be careful that, because the answer will be in positive, but you have to be careful that to give it in a negative sign. So you have to be very careful working with these angles. So we have the two forces in the Cartesian vector form. The rest is just simply by finding the resultant component, so adding the x component and the y component. So for the x component and the y component, you get the force in Cartesian vector form. Notice here the negative sign. So we know that the resultant of the z resultant of the force is directed towards the negative side of the axis, of the z axis. Followed by that, we find the magnitude, which is square root of a sum of the squares of the three components, and that's the magnitude of force. Now the direction has to be represented by the angles alpha, beta, and gamma. In a 2D, we had only one angle, but in the 3D, we have to represent the force direction using its alpha, beta, and gamma. So remember the cosine alpha is the force component in the x over its magnitude. Then also we have the x component and we have the magnitude. Then we can get the cosine, the angles. So inverse cosine of a x over its magnitude, y over its magnitude for the beta, and then z over the magnitude. Notice we use also the signs to give us exactly what is the angle. If we need to represent this in a 3D image, then we draw the 3D axis, and then you have the force, the resultant force. This is the alpha, which is measured 86 degrees, and then beta is 13 degrees, and then gamma is this for angle measured between the z-axis. And so notice that it has to be down. So if we draw these lines, then the force is actually in the negative side of the z and the positive of the x and y. Very careful. You have to be when you write these angles, especially if you the direction of that, because any mistakes, like example using here the positive sign, then it means that this angle or the force would be on the other side of that or on the positive side of the z-axis. This wraps up this session, and thank you, and see you in the coming session.